and welcome to the video. And until now, we saw the response of our system to step and the sinusoidal inputs. And now let's say we have a system h of s, and we have an input of Vp cos omega t. So this is basically a sinusoidal input, and we can write our output in this form where it represents that the output will be the magnitude or the gain times Vp cos omega t minus of the angle or the phase introduced by our system or our transfer function. So we have two conditions. So basically in our previous video, what we saw was this kind of a bode diagram and magnitude versus phase plot. And we were talking about these parameters. So let's take the value omega u by k, and for the frequencies very less than omega u by k, we can say that our gain or a transfer function is nothing but k, and the angle introduced can be written as this value. And how it came? So basically we had our angle which was minus tan inverse of something, and if that something is very less, so for very small value of x, tan inverse x is nothing but x. So that's how we came to this conclusion that the angle introduced or the phase introduced due to our system is omega k by omega u, when our omega is really lesser than omega u by k. So our V out can be written in this format, and by simplifying it further, it can be written in a form where we have the amplitude k times the Vp times cos. If we take omega out common, we are left with t minus k by omega u. So k by omega u is basically the delay contributed, or the delay contribution due to the system, and whose value is k by omega u. So now in this condition, where the value of omega is very greater than omega u by k, we have this condition. And basically after the pole frequency, the transfer function magnitude comes about omega u by omega, and the phase introduced is nothing but minus pi by 2. As we saw here, the phase introduced is minus pi by 2. So when omega is very greater than omega u, V out can be written by introducing these values in the equation we derived for V out, and we can say that the amplitude of V naught, or the output voltage, has nothing to do with the gain k when omega is very greater than omega u by k. And that's how, like, omega u by k is basically differentiating between the ideal and non-ideal behavior of our op-amp. So again, coming to a very important and crucial factor of our system, which is basically a loop gain. And to find a loop gain, or to derive something for loop gain and see its importance, let's do one thing. So it's related to our loop anyway, and it is something which we introduce to our loop and what we get back through our loop. So basically what we'll do is, let's break the loop from here at the input of our integrator, and let's apply V test at the integrator and analyze what comes back from the loop to this point itself. And let's say it is a V return, or the return voltage. So what we'll do is, we'll reduce Vi to be 0, and after applying V test, our V naught will be coming out nothing but omega u by s times V test, and thus our feedback will be nothing but omega u by s V test divided by this factor k. And here we get at this point, as Vi is 0, so 0 minus, so we get the minus sign over here. And at this point we return, or the return voltage is nothing but omega u by k times s multiplied by V test, and that's how we get our V return. And when we talk about loop gain, so basically our loop gain is nothing but, to remove the effect of this minus sign, we have V return divided by the V test, and the value comes out to be omega u by k s, and that's how we define our loop gain. And let's talk more about the magnitude and phase plot of our loop gain. So the magnitude of our loop gain becomes unity at the frequency, which is equal to omega u by k. And what's the significance of this omega u by k? So to have a negative feedback loop, a significant amount of feedback has to be there, and loop gain signifies the quantity of our feedback. So beyond the value of omega u by k, practically there is no feedback. So for omega, which is lesser than omega u by k, we have a strong feedback, and the amplifier tends to behave ideally. And now, like, let's talk about the error. So error, to become very small, the feedback has to be very strong, and thus the value of omega u by k, or basically we can call it omega loop, which is unity loop gain frequency. So that value has to be larger. So how? So basically, to be able to have larger bandwidth, to have a larger range of frequency, let's say, where our loop will behave and give a proper feedback or a proper gain, let's say where the system behaves ideally, we need to have a higher value of omega loop for higher bandwidth, or let's say higher or a longer range of frequencies. So that's about the loop gain and its crucial importance in designing a system. So basically, now what we say that we have to sense the difference and basically integrate it, and a block which does sensing the difference between input and the feedback and also integrates this difference is known as operational amplifier. And this is how its symbol is. So basically, we have studied op amps in our basic analog circuits and other subjects as well. So basically, the configuration over here is a non-inverting configuration, where the op amp itself has a unity gain frequency, which is omega u. And as we have designed our negative feedback system, so let's say this is our negative feedback, and we are familiar with this resistive divider. So basically, the transfer function comes out to be k by 1 plus s times k by omega u. So here rises the concept of ideal op amp. So basically, what we are doing is, if we go on increasing the value of omega u of this structure, the bandwidth of the system will basically increase. And if we set omega u to be infinity, so bandwidth will be infinity, and for all frequencies, so the gain of the system will be k. So why this concept of ideal op amp is useful? So it is useful block for analysis. Let's say we have a circuit, any op amp circuit to analyze, and we can assume the op amps to be ideal, meaning the input voltage or the VE to the integrator or the difference is zero. So these two nodes are at zero voltage, and then analyze the circuit. And after that, we can put in all the non-idealities or the non-ideal details to the circuit and analyze the circuit. So that's all for this video, and thank you for watching.